Hello and welcome. Today, we're looking at a vital piece of our clean energy future, grid-scale energy storage. As we rely more on solar and wind, we need ways to store that power reliably. Lithium-ion batteries are common, but for truly massive, long-duration storage, they have cost, lifespan, and material sourcing challenges. This has spurred innovation into a whole world of beyond lithium-ion technologies. Let's explore some emerging contenders. First, flow batteries. Unlike typical batteries, these store energy in liquid electrolytes in external tanks. Need more energy? Just use bigger tanks. Vanadium redox flow batteries, or VRFBs, are a mature example, offering long lifespans, often over 10 or 20,000 cycles, and great scalability for 4 to 12 hours of storage or more. They're non-flammable, and the vanadium can be recycled. The main hurdle is the initial cost of vanadium, though research is ongoing to reduce this. Zinc-based flow batteries, using zinc bromine or zinc iron, are also gaining attention as they tend to be cheaper due to abundant zinc. However, they face challenges like zinc dendrite formation. Other chemistries like all-iron or organic flow batteries are also being developed. Then there are sodium-ion batteries. They work like lithium-ion, but use sodium, which is far more abundant and cheaper. This makes them a strong candidate for stationary storage, where sheer energy density isn't as crucial as for cars. They also perform better in cold temperatures and are generally safer. Commercial production is starting to ramp up. Metal-air batteries are another interesting group, using metals like zinc, iron, or aluminum reacting with oxygen from the air. Iron-air batteries promise very low material costs, potential for long discharge, but need improvements in efficiency and cycle life. Zinc-air batteries also offer high energy density and low material costs, but rechargeable versions for grid-scale use are still under development. Don't count out advanced lead-acid batteries. Innovations like lead-carbon designs are boosting their cycle life and performance, making them a cost-effective option for certain grid needs. High-temperature batteries like sodium-sulfur offer high energy density and have been used in grid projects, but their high operating temperatures pose safety concerns. Molten salt batteries, a similar high-temperature type, aim for improved safety. Beyond these chemical solutions, there are fascinating mechanical and thermal storage options, especially for very large-scale needs. Pumped hydro storage is the current champion, using surplus electricity to pump water uphill and releasing it through turbines when power is needed. It's long-lasting, but needs specific geography. Compressed air energy storage, or CAES, uses excess power to compress air into underground caverns or tanks, then releases it through a turbine. Liquid air energy storage, LAES, cools air until it liquefies, stores it, and then regasifies it to drive turbines. LAES isn't tied to specific locations like pumped hydro. Gravitational storage is another concept, using electricity to lift heavy masses like concrete blocks, then lowering them to generate power. Thermal energy storage, or TES, stores energy as heat. Molten salts, widely used in concentrated solar power plants, can store heat at high temperatures to produce steam for electricity on demand. Simpler systems use concrete or rocks. Finally, there's hydrogen energy storage. Green hydrogen, made with renewable electricity, can be stored for long periods and then converted back to electricity using fuel cells or turbines. Hydrogen is versatile, but faces challenges with round-trip efficiency and storage costs. So what's the path forward? A renewable energy future needs a diverse toolkit of storage solutions. Lithium-ion will still be important, especially for shorter durations. But for longer storage, lower costs, better safety, sustainable materials, and longer lifespans, these alternative technologies are key. Continued research, development, and supportive policies are vital to scale them up. The future isn't about one winning technology, but a smart mix, tailored to specific needs and locations, building a truly resilient and sustainable electricity grid.